Okay, welcome. Okay, so assignment 5, deadline is this Wednesday. Assignment 6 has been uploaded. Deadline is next Wednesday. Then let's assume the midterm will proceed as usual. At the moment, I cannot say too much, so let's assume business as usual. But it will be an online exam with invigilation. And if you really have difficulties, any difficulty, I will consider your case as much as possible. Okay, so don't worry too much. The message is don't worry too much. And I want you to know that we are together. So we will be able to get through this together. Okay, so just be reasonable. Everybody at this moment, let's just be reasonable. Okay, so at the same time, I would like you to really try to respect the assessment scheme. So if you are able to come, it's always good for you to do the midterm, because the idea is this: the midterm will cover the material up to the midterm. So this is a chance to consolidate your understanding, so we can do this second part of the course, namely the statistical physics, more smoothly. Okay, so this is the point. I always want to view it not as assessment, but rather we should see as an education process. Okay, so now again, I don't want to spend too much time talking about this. Things can change anytime, and it will be a waste of my time if I plan too much, and in the end we have to come up with a plan B. Okay, so let's see how it goes, and assume things will proceed as usual, which means the midterm, our original plan is to have it on 14th, right? It's Monday. Okay, so do you have question? I see no chat, no. Okay, so I would rather let's talk about something more interesting. Okay, namely thermodynamic. Okay, last time we talked about phase transition. Last time we got to this point, it's about the order of a phase transition. And I use a new bit paper, and I don't know how to, I should have prepared the writing, so I don't have to write it again. So just bear with me, just give me a little bit more time. We already got to this point about the classification. This classification is about this business about first order, second order. And we know that if we go through the treatment we have done so far, we are actually describing a phase transition, which is a first order transition. Okay, so phase transition is a big subject. You can find the entire book, like 500 pages of material on phase transition. Okay, so this is something people spend a lot of time to study, and what we have studied is a very small subset, and this is a first order transition. And why first order? This has to go back to this very old classification, and I'm going to write it again. So this is the order of a phase transition. Okay, and this is the order of the lowest differential. Is the order of the lowest differential, differential of G, Gibbs function, that shows discontinuity. A discontinuity. Discontinuity where? Discontinuity at the phase transition. At the phase transition. Okay, so the first order differential for our case, we know very well. This is the first order differential. When you write down the differential form of Gibbs function dg, you know this is related to the change of temperature and the change of pressure. These are the natural variables, and from there you can find your first order differential, and these are the first order differential here. And we know this quantity must jump. Again, just think about your solid to liquid phase transition for H2O, and you know there's a volume change involved, and you know from school that there's a latent heat involved, and when you have a latent heat involved, that is due to the fact that the entropy has changed, and that's why you need to supply additional heat, and that is related to all these are related. Okay, so these are this must show discontinuity. Okay, I would just loosely call it a jump for the first order. And for second order phase transition, this will not jump. Okay, so they will only show some anomaly. And that brings me to this figure. Okay, so this is a figure from Blundell and Blundell. This is B&B. And these are my comments. And so here, the first row up here is the first order transition, and this is second order. Now, second order phase transition is actually rather common. You don't, for example, a superconducting phase transition is a second order phase transition. Particularly when you talk about zero field, it can be shown that if you apply a magnetic field, things will be more complicated. But at zero field, this is a first is a second order phase transition. So this is something important actually. Don't get it wrong. That second order phase transition is not realistic. It is very realistic, and you see it quite a lot. Okay, so the first order transition, suppose, let me assume this. Now, the first comment is this: when you want to discuss things like this, this has to be interpreted as some kind of intensive quantity. So this better be given in the form that the system size is taken into account. For example, you can have a joule per mole, joule per kilogram, joule per particle, and that is the way to interpret this. And with regard to this, I already stressed this several times, and I really want you to get 100% on top of this. So if you look at the newest assignment, the one I uploaded today, you will see that I designed a problem for you. I designed a problem that allows you to appreciate the fact that at the phase transition, something happens to the Gibbs function. And you have to do it in a very careful way. It's not difficult, but you need to be careful. And all the numbers I just managed to extract from Wikipedia, for example. And then I use the theory we developed in this course. We'll be able to get very nice, consistent results. So this is something I hope you will appreciate and enjoy that problem. That is in the newest assignment. Okay, and that is related to this business, the business of Gibbs, as well as the relationship of Gibbs with other thermodynamic quantities. Okay, how do you appreciate this? So the thing is, suppose you are able to do calculation. Let's say this is a liquid phase and this is a gas phase. You have a lot of good knowledge about your gas phase. You have a good computer. You have all the assumptions you can make in a very reasonable form. And suppose you are able to do that much, you'll be able to calculate Gibbs function as a function of temperature, right? So suppose you are able to do that, you get this line. You calculate that for your gas as a function of temperature. Right? Therefore, this kind of calculation, there's no limit for the temperature range as long as the assumptions are valid in this range. Okay, so that's to say you'll be able to calculate the Gibbs function as a function of temperature for the gas phase. And for the liquid, you can also do the same, and you do the calculation. Maybe you are able to extract a lot of experimental data from your liquid, this particular kind of liquid, from the same substance. You know a lot about that, and you can do calculation. So you get something maybe that looks like this. Okay, so the way to see this is this: the liquid phase. You will have, hypothetically, you have this kind of Gibbs as a function of temperature, and for the same substance, the Gibbs function that is the lower will win. That is the phase you will stabilize. Okay, so for the liquid phase, now your theory tells you, okay, below certain temperature, the Gibbs function for the gas phase, the blue one is higher than that of the liquid phase, and therefore the liquid phase is a stable one. The lower the phase with the lower Gibbs function, specific Gibbs function will win. Okay, and following the same argument, above that, there will be the stable phase will be the gas phase. And this tells you the story of a phase transition. So the phase transition happens when these two curves meet. And that is to say you have a phase transition here when they meet. Okay, and this, of course, is what we have derived when we discuss the phase transition and to get to the closest Clapeyron equation. This is where the specific Gibbs specific Gibbs function Gibbs are equal. Okay, specific Gibbs function of the gas phase and the specific Gibbs function of the liquid phase are equal at the phase transition temperature. Okay, so now from here the rest just follow. You do the first differential. In this case, if you now I kind of draw more lines for you. So if you then summarize everything, you will see the curve originally presented to you. The Gibbs function shows a kink. Okay, for this case, for this pure substance, whatever this pure substance is. Okay, so from here, this is the overall Gibbs function you get, and this is your TC, critical temperature, and you take the derivative because there's a kink, so the volume has to jump, and because there's a jump, discontinuity, then this point is non differentiable. The next derivative has to diverge, so the heat capacity shows this behavior. So this is something we can measure well, heat capacity. Actually, volume we can also measure reasonably well. We do X-ray diffraction, for example, but this depends on the nature of the phases. If it's a solid, if you have a solid to solid first order phase transition, you can do X-ray diffraction, and that is something rather straightforward for you to get the volume, and then you see the volume will jump. Okay, but heat capacity is something, as I say, readily measurable. Okay, for the second order, everything is much weaker. So you actually have something is happening, but you just cannot see. When something is happening, you cannot see. What is your mathematical trick? You just keep taking derivatives. Okay, so it looks smooth. You might say there's nothing here, but how do you detect this change? You look at the derivative, and the derivative indeed shows you the volume has to change slope, right? The volume will shrink faster as you cool down compared with the the high temperature phase. Okay, but the volume remains the same at the phase transition temperature, and therefore you see this kink. And you take the next derivative, and that will give you the heat capacity, and the heat capacity will show a jump, right? You differentiate kink and you get the jump. Okay, and this is all nicely summarized in this table from Atkins. This is from Atkins, and these are all in specific quantity in lower case, but it doesn't matter as long as you know what you are doing. This is really written in the specific form. So the other things that we mentioned heat capacity, but there are other things you already met. They will also jump at the second order phase transition. So for the first order, you know entropy has to jump at the phase transition, volume has to jump. For the second order phase transition, entropy is continuous and shows an anomaly, but there's no discontinuity. Likewise, the volume is also the same. And for the second order phase transition, what else can you do to detect it? You can also try to measure other quantities. For example, thermal expansion. This is the same symbol, and this is thermal expansion. And you can also have compressibility. Okay, this will be related to the second order differential that will jump. Okay, and then you if you have an even weaker phase transition, you have to keep doing derivative to identify the jump. Okay, so loosely, in modern literature, we don't really want to go down this list. In modern literature, we call this continuous phase transition. And this is the first order is first order. Higher order phase transition, we call it continuous phase transition. Continuous phase transition. Okay, I think this is readily appreciable, right? You can see why this is continuous. Even for second order, you know this is continuous. Right? Volume is continuous, entropy is continuous, it doesn't jump. And third order is even weaker. So you can kind of mathematically understand this, right? Everything is just get displayed by one column compared with the first order. If you look at the second order, you have to find the kink in the first order differential, whereas in the first order transition, the function itself is already showing a kink. Okay, so for the higher order, this will get washed out even more. It would just appear even more continuous. So this phase transition will be even harder to detect. Okay, so this is some stories about how to identify the order of a phase transition. I want to do a little bit more by asking something a little bit hand waving, but I think it's good for our purpose, which is I want to ask, how do we know which phase to choose? So this is again, how do we know which phase to choose? Our guidance is provided by the Gibbs function, and I will use a symbol G, capital G again, but this is best, actually not best. You must interpret this as some kind of specific quantity. For example, Gibbs per mole. Okay, this is the quantity you study. This is the thermodynamic potential function you study. Okay, and for this discussion, I also want to make life simple. I just want to look at a pure substance, for example, H2O to H2O, but in different phase. And I also want to look at the limiting cases to extract feeling about this business. So limiting case means I want to look at G as a function of temperature only for solid and gas. Just to appreciate, the physics behind. If I add liquid, it's a lot harder to model, and at this level of qualitative explanation, it doesn't give us any more insight. Doesn't give us any new insight. Okay, so let's at least try to appreciate why at low temperature we stabilize solid, at high temperature we stabilize the gas phase. So this is related to that picture here, right? It's related to 2 pages ago. This one. So we need to be able to see why the specific Gibbs function for the solid and the gas can cross. Okay, and then you know how to trigger a phase transition. Thermodynamically, this is good enough. Okay, so how do I look at this? What is the Gibbs function? The Gibbs function, let me remind you, the Gibbs function is written like this. Okay, so this is how we define the Gibbs function 2 chapters ago, or sorry, actually last chapter. Okay, so we want to look at this and to see how we can understand the competition between the Gibbs function for the gas phase and the Gibbs function for the solid phase. So we naturally need some kind of figure, very hand waving, but let me try. Let's try this. Okay, so I will put 0 here. This is my Gibbs function. I put 0 here, and this is also 0. The temperature is 0 here. Okay, what is U? U is the internal energy. Without knowing the detail, I can at least say this much. Okay, in a solid, what gives you the internal energy? So in the solid, you have all the atoms, they are very close together. Okay, the reason you can form solid is because all these atoms are locked together and they interact with each other, right? Because of this interaction, they want to form this lattice. They want to they are happier to be in a order form. Right? If you try to displace one away, you cause more energy. So this is what we call the cohesive energy. Okay, so this is what we write for the internal energy of the solid. So for solid, we have the phenomena of cohesive energy, which brings all the atoms together. So this is responsible for the interaction between, actually interaction among all the atoms. Okay, and this quantity in solid is large and negative. So this is large and negative because of the close proximity. Okay, and this is now for solid, I don't know where that is. Let me just assume it's somewhere here. Okay, so this is my solid. Okay, so this is solid. And for gas, what do we have? For gas, this will be if you argue it this way, for gas, all these gas particles are very, very far away, and you can just immediately realize that the interaction must be weaker, and it's a lot weaker. Okay, now suppose you are able to stabilize gas at 0 temperature limit. This is what you will see. Okay, the internal energy for the gas, you will not be able to gain from this cohesive energy, and you will be very many order of magnitude weaker. So for gas, the internal energy will be a order of magnitude smaller. So orders of magnitude smaller. Okay, so at zero temperature, look at this. I actually went a little bit faster. At zero temperature, the second term doesn't really help you. Zero, you just kill it. Okay, and PV term maybe, but it's a small effect. So let's ignore it, or just qualitatively, we can say it like this: the Gibbs function of the solid is dominated by the cohesive energy, which enters through the internal energy term. Okay, and for the gas, you will have something which is order of magnitude smaller. So I would just practically take it as zero. So this is my gas. Okay, so this is at low temperature. And how do you possibly stabilize the gas phase? If you look at this, you can only have one reasonable solution, and that is to take advantage of the second term. Why? Because if you look at gas has large volume compared with solid. So this is actually bad news for the PV term. This PV term is actually bad news for gas, right? Because gas has a lot larger volume. So the PV term will be large compared with solid. You are already so much smaller. Your Gibbs function, your specific Gibbs function is already so much smaller than the solid. And if you want to, I mean you should think of it as going towards a positive side. So this is large and negative. So this is the winner for the solid case. So if you really want to stabilize the gas phase, you can only take advantage of the second term because of this negative TS. Okay, so that is to say you will be able to imagine having something that behave like this if your second term is working. And how do you make the second term work? This, if you want to really predict something, you need to put in numbers, but in the very schematic way. The only way we can do this is to imagine having a temperature T which amplify the second term. Solid has lower entropy because solid is order, right? Gas is a little bit disorder, so it has larger freedom to explore. So S of gas can be expected to be larger than solid. So solid has lower entropy. So for the entropy term, solid in general has a lower entropy. Okay, and this is something you can gain, you can use, you can take advantage. So for gas, I know my entropy is larger, but because this is order of magnitude difference, the only way I can boost the second term is to go to high temperature. Okay, so this will hopefully grow at sufficiently high temperature. And for my solid, it will also go down because of this negative term. And we assume the PV term only give a small correction. And you will see something like this. So at some point it will cross, and this is where you will be able to stabilize. You have a phase transition. This is TC. Okay, so this is at least you can appreciate. If we look at only the solid and gas, this is entirely possible. In reality, of course, you will have a liquid phase, or you can have other solid phases. You will have more complications, but these are details. These are something that people can do very well these days. For example, this is a figure I like. I found this from this textbook, not our textbook, but this textbook has a lot of data. And again, the first thing you should notice is this is again given in the unit of joule per mole. So this is a specific quantity, an intensive quantity. And if you look at only the curve for solid and gas, you will see this is more or less going towards the same trend as what I explained earlier. If you look at this figure, hopefully, if you look at this figure, hopefully now you can have some feeling about this. Right? Why do I draw it like this gas curve? Why do I draw it with such a steeper slope? Why do I start from 0? And for solid, what happens here? Why do I start from here? Why do I draw a curve which is gentler? And the reason is given earlier in the past 10 minutes. Okay, but this figure is done, is constructed with a more realistic calculation. This is, all these points are rather meaningful. It's based on a good simulation. And you see what happens here. And this is for potassium. At the lowest temperature, you stabilize the solid phase because solid has the lowest Gibbs free energy. Okay, and liquid is a little bit higher, but not too much. And therefore, if you warm up, at some point they will cross, and these two curves will cross. Solid and liquid will cross. And therefore, you enter the liquid phase. If you look carefully, this is continuous. Unfortunately, they didn't color code this. So you will see, I will draw it and then I will erase it. You will see this is the solid. And then here it goes through a kink and it enters the liquid. It enters the liquid phase, which is always the lower one. Okay. And at this moment, you don't care about solid anymore. It's not relevant. You are stabilizing the liquid phase, but calculation will give you all three. And then further, when you go beyond 980 Kelvin, you will enter the gas phase. So this is how it looks like. So if I summarize it, it will look like 0 is somewhere here. 0 is somewhere here. And the overall Gibbs function will look like this. Like this. Okay, and this is the figure that shows you there are two first order phase transitions. And this is the temperature. Now this figure is also available in the note, but I don't want to I will keep it like this. I will give you another page later when I arrange for the note, so you get the original figure. Okay, so this is fun stuff. Actually, is very. There are a lot of calculations done like this. For example, if you want to investigate a new compound, how do you know it is stable? One thing you can do is you calculate all these Gibbs function for different phases. You have different structures. You can put in a lot of data. There are a lot of experimental data out there, and if you know how to do the calculation and extract data from the database, you'll be able to do this kind of calculation. So actually, this book, this figure, where they present this figure, the book is actually talking about how to do this kind of calculation. How do you get this one point here, and how do you calculate the entire phase diagram? And this is a way for you to predict a new structure and find a new state of matter. You have maybe you make a new compound. You calculate all this to see whether there's a possibility of stabilizing a different phase. Okay, so that's all for this chapter. Do you have question about this? Okay, then I move on. We will talk about actually this is chapter 7. Chapter 7, I'm going to okay, I add one more slide first. So first I need a copy of this, then I need a new slide. This is 6, 7, new slide. Okay, we are entering the last, the final chapter of thermodynamic. Okay, so this is and after that we are going to do statistical mechanics, and therefore this is the last chance for us to look at slightly different systems. And I'm going to, the title of this chapter is Beyond a Simple PV System. So here in this chapter, I want to talk about I want to talk about this. I want to talk about elastic rod or wire. This is actually fun. I'm going to now I don't know whether you have done this kind of experiment at home. If you take a rubber band, right, elastic rod, you can think about it as elastic wire. Elastic wire. You take a rubber band. This is a very good thermodynamic system. You take a rubber band, not too small, otherwise you hurt yourself. Something a little bit thicker, and you can pull very quickly. You pull very quickly and pull it on your lips. And what do you feel? Right? You take a rubber band. Let me say this again. You pull, and you put it on your lips. What do you feel? Okay, so this is, remember this question. If you have done this experiment, you can also tell me the answer. It's also nice for me to see your intuition. Maybe you have done it, I don't know, in the past 15 years of your life. When you're too young, you're not allowed to do something like this, but maybe you're naughty enough to begin to play with things like this. What happens when you do that? Okay, and I will give you a concrete answer to this question later. And the other thing I want to talk about is a magnet. It's a magnetic system, and more accurately, this is a paramagnet. This is also cool. Now, once you understand this paramagnet, you can actually use it to do cooling. So this is something important for cooling technology. Cooling technology. This is something important in this sense. We talked about liquid helium last week. We use liquid helium to cool, but liquid helium itself is bulky, is hard to transport. Now, suppose you want to cool something in the outer space. Are you going to transport 200 liters of liquid helium with you, or you have other technology? If you go to outer space, very likely you can take advantage of the ambient condition, right? So why do we even need to do the cooling? There are lots of reasons I can give you. For example, you might be sending some sensor to the outer space. You want to collect some data, and you want to decrease the temperature of your sensor. Why do you do that? You do that to decrease the noise, right? If you have cooling, if your sensor is operating at a lower temperature, your signal will be your signal size might be the same, but the noise will be greatly reduced, so you get high sensitivity. Signal to noise ratio goes up, and therefore there's all kind of justification to do cooling. Another reason is maybe your sensor is based on a superconductor, and your superconductor is operating at a low temperature, very low temperature, and you need to cool down to below the transition temperature, so you can take advantage of the superconductivity. And therefore, you want to come up with a cooling technology that is practical. And what is a practical cooling technology in this sense? In this sense is what you don't want to is to take a lot of liquid helium with you. That is not very economical. So you can take advantage of the magnet to do cooling. You can cool down to millikelvin this way, millikelvin. Okay, and liquid helium, it gives you 4.2 Kelvin. And actually, in the Earth, in our lab, we actually combine the two. We have the liquid helium as a first stage cooling. We cool to 4.2. How do we go lower? One possibility is to use this kind of thermodynamic. And this is the thermodynamic you learn in this course. And you will be able to answer, you will be able to appreciate that this technology. Okay, and then after I talk about this, I want you to compare this with our gas expansion. So this is my outline for you. So after you do this, I want you to compare with gas expansion of the PV system, which is something you learn all along. Okay, so you have a nice picture. Hopefully you build it up yourself. If not, I will give you the picture comparing the rubber band, the magnet, and the gas expansion, and you will see they are actually the same thing. And that is why what I written here in green, we spent 6 weeks to develop. Okay, and the idea is you can switch gear and to look at the elastic rod and to look at the paramagnet. Okay, so this is my grand plan for this chapter. And if you have downloaded assignment 6, you will see the coverage for the midterm, which if we really can conduct the midterm, I actually want to switch the order a little bit. I don't want to talk about the paramagnet first. I don't want to talk about elastic rod first. I want to start by talking about an open system. Okay, but open system, what do I mean by beyond a simple PV system? What I meant is this, where I'm going to talk about an open PV system. And that is a good place to talk about because of our treatment of thermodynamics. We just finished the treatment of thermodynamics, so this is a good place to talk about an open PV system, and you will see why. Okay, so this is first. Talk about this first. Talk about this first. This subject first. Okay, now open system means I really allow particle exchange. I can allow the particle to enter my thermodynamic system. I hope you appreciate that this is really what happens for the phase transition, right? If I have a phase transition, if I look at the entire system, which I drew earlier, I look at M1, phase 1, phase 2. I close the whole thing. Particle cannot exchange, cannot enter. This is a closed system. But if you look at the solid, it's the one of the phases, let's say liquid. This is actually an open system. Why? Because some of the particle in M1 can leave and go to M2. So particle can exchange, right? So this is, I can draw it this way. I can schematically draw this boundary as some kind of a membrane that can either move up or down, can exchange particle, and can exchange heat. So this is what you have actually been doing. And that is why if you read Steen decided to develop phase transition after talking about the open system. We just chose to do it the opposite way. Okay, so I hope this is clear to you that you can view this as two open systems in contact. Okay, so how do I deal with particle exchange? I just gave you 3 ingredients, right? I told you you can have heat can flow, volume can change, you can exchange volume, you can exchange heat. Okay, so you already know how to deal with these 2. So that is what you have done so far. And the first law for that situation is this. Okay, this is the fundamental relation we develop. And this part is, if you stop here, what do you implicitly say? What you implicitly say here is, this is a closed system with constant n. The number of particles is constant. Okay, And now you know the recipe. I think I stressed this before, right? The closed system, we always do not put this constant n in the when we write the partial derivative, but this is assumed. For the open system, you simply have to take into account of this. You have to allow the particle number to change. You can bring new molecules, you can bring new particle. And how do you quantify this? You quantify with something which I will keep the symbol mu. Okay, and this mu is chemical potential. Okay, another way, another scenario is this. If you have black body radiation, black body radiation is a very interesting system. You have your enclosure, you have your cavity, and this is your cavity. You can close it, it doesn't matter, you can close it. But what do you have inside? You have photons. Photons is a very interesting so you have many photons here. So this is let's say I have a black body radiation. So for photons, because this is a particle without mass, you can actually create them. So if you know how to create photons, then particle number is not conserved. Then you can actually see as an open system because I can add more particles inside. Okay, so that is another scenario where you can understand that open system is actually quite common. And from here, we can do a lot of thermodynamics too. And we are going to do this in the statistical mechanics part. We are going to extract the radiation law, the Stefan Boltzmann law. We are going to get all this radiation law over there. Okay, but here is a good point to mention to you that photon is you cannot just see this as a gas of ideal, a collection of ideal gas. Photon is a very interesting species. So for example, for the ideal gas, if I change this label to ideal gas, what do you have? You know, you have the internal energy of the ideal gas is a function of temperature only, right? This is something we learn. So if I have black body radiation, what do I have? If I have black body radiation, what I have is something different. I have U. This is a lowercase u, which is the energy density. Right? So I will define it. I will call this U, big U. I will. How should I make it big enough for you? Big U divided by volume, and this thing is a function of temperature only. Not to be confused. I'm sorry. I try to write very carefully. So I have mu, which is the one with the tail, and this U is a capital U, and this U is a lowercase u. So I hope it's clear enough. So this is the internal energy density, and this internal energy density is a function of temperature only. So this is a tiny change. But now look at this. How do I make the density constant? If I have a isothermal expansion, let's say I suppose I have a way to change the volume in an isothermal way. If I change it isothermally, in order to, now the volume will go up, right? But I need to make the density constant. This is a property of black body radiation. Okay, density is a constant, volume I increase the volume, then my internal energy has to go up. Right? And if I see this internal energy to be a property of the particle number is not conserved. And therefore, I have to be able to create more photons in order to fit in this energy. Okay, so this is fascinating stuff, and we can look at this later. And you get from here, from this argument, actually, from what I just say, you can do the thermodynamic and get the Stefan Boltzmann law, right? That tells you the radiation heating goes as T to the 4th. Okay, I sidetracked a little bit. Now let's come back to here. So coming back to our open system, what do I have now? So what I can do is to look at this mu. This is a new thing we introduced. The rest are quite familiar. You have seen many times. So let's see what this mu is doing. So this is a chemical potential. When I write it like this, so let me make the note complete. So this is a closed system with constant. So I have to add this, must add if system is open. Okay, but I still talk about PV. So the work done is still due to PDV. Okay, so if I look at this, I will have my internal energy. We'll take the natural variable as volume V and particle number N. Okay, and our usual definition is this. Then we will have our mu will be the partial derivative written like this. S and B. Okay. Now, and the rest also follow. If I have Helmholtz function, if I don't want to control the entropy, I would like to look at the temperature instead. Then I have to discuss the Helmholtz function, and the definition is the same. I will have the F will be U minus TS, but now my internal energy will be more complicated, because once I take the du, I cannot ignore the mu dn term. Okay, I will let you do it yourself. If you just follow the standard trick, you get this. Okay, PDV minus S dt, and these are the same as before for constant n. And now I have this mu dn. Okay, and in that case, your mu will be given by this. So I will have T and V. Okay, so it really depends on the constraint. If I have a different constraint, let's say I look at the I know how to control my temperature and pressure, then the constraint will request me to look at the Gibbs, right? So you follow this again, write down the definition, and there the mu in that case will be given by this. Okay, so here this mu is the conjugate variable for this particle number. Okay, let's see what we can say more about this mu. Actually, okay, mu, the role of chemical potential mu. Okay, the best way is to come up with a system to investigate equilibrium. So I will look at now. I will look at this. I want to look at this picture up here, this liquid, and this one. Okay, but I'm going to simplify it to give me the outcome I want quickly. You can generalize it if you want. So I will look at the system that can exchange heat and particle Okay, I do not want to exchange volume. You have seen this similar argument not long ago. If you handed in your assignment on Friday, you have seen it, right? This is assignment 4. And now our first law, our fundamental relation has the other term include. So you can already guess what we can do, right? So for simplicity, I want to ignore volume change. I will set dV to be 0. So the picture will look like this. I would draw the same picture again, but I draw it horizontally. So rather than having a membrane that can move, I will fix this. I will still allow. First I will take 2 subsystems in contact, and then I close it to the rest of the universe. So this is my universe. Okay, and I'm going to label this as 1. This is 2. I have 2 systems. They are in contact. I do not allow the volume change, so I make this into a rigid partition, and this partition is has a property that I can exchange a particle. The particle can cross, and I can also exchange heat. Okay, so that is the setup, and this is enough for us to gain enough insight. Okay, so I'm going to write ds. I will just rearrange my fundamental relation. So I have TDS term. I move it to I just look at the TDS term really and rearrange it. I will have du over T plus PdV and plus PdV over T, and finally I have this mu T over D Tm. Okay. So for this system, I have the total number of particles has to be a constant, right? I have 2 subsystems, but I cannot gain particle from outside. So this has to be a constant. So this has to be a constant n, right? So therefore, this has to be 0. Okay, and this allows me to write this. And likewise, the total internal energy is also a constant. There's no way to gain total internal energy. I cannot gain particle from outside. This volume cannot change. So maybe for I will call this rigid as well. This is a rigid total system, and no heat can enter because I close it like this. So this is also 0, and therefore I will have du1 is minus du2. Okay, so now I can apply the second law. The total entropy of the universe has to be greater or equal to 0. And the total entropy for an infinitesimal change will be due to the sum of these 2 terms. Okay, this cannot decrease. Okay, so I come here and I already have this line up here. I know how to write ds1. So ds1 will be due to du1. So if there's an infinitesimal change of internal energy for system 1, this is what happened. And dV is 0. I don't care about dV anymore. And then I have mu1 and T1. Okay, and then I have dN1. This is for the first system. And I just copy and then give you the second system. So I have du2, T2, minus mu2, T2, dN2. This will be the sum. Okay, and now let me rearrange. I'm going to eliminate N2 and U2. Okay, using these two line here. So I will have 1 over T1 minus 1 over T2, right? Minus 1 over T1 minus 1 over T2. I move this one here, combine with du1 because I know du2 is minus du1. Okay. And likewise, I will do the same with the chemical potential term. I will have mu1 divided by T1 times dN1 times dN1. And then this will become plus because I use this result. So if I change to dN1, it will be plus. So if I put everything in the bracket, it will be minus. This you can check. This is if I make a mistake, shout. Otherwise, please always check. I do make this kind of mistake. Okay, so this whole thing has to be positive or 0. Where are you? Yeah. Okay, so now you see you have done something in assignment 4, so you know this is familiar. Okay, now be careful of my logic. I want to argue it this way. Now I want to look at the situation where the two systems are in equilibrium, in thermal equilibrium. Okay, so what can I do? I can then set T1 equals T2. I can also I don't want the complication of volume change. I also now do not want the complication of the temperature change. I have my subsystems. I will set them to be at the same temperature. And now you can see what happens. If they are the same, the first term is gone. T1, 1 over T1 minus 1 over T1 is gone. And now we are ready to discuss the situation based on the second law. The second law requires this to be positive or 0. Let's consider the case that they are positive and not 0 first. Okay, so if you want them to be positive, then dN1 better be positive. If dN1 is positive, if you want the product to be positive, this term has to be positive, right? So if this is positive, then minus mu1 over T. Sorry, this whole thing in the big brackets must be positive as well. Okay, and in this case, you can only satisfy this if mu2 is greater than mu1. Okay, so then mu2 is greater than mu1, and you know the opposite is also true. If I will set dN1 to be negative, I have to flip this inequality. Okay, and now let's look at the situation a little bit. What do I mean by dN1 is positive? So dN1 is positive means system 1. This means system 1 gains particle, right? Particle flows to system 1. How can I drive this flow? I have to drive this flow if I create a potential difference. And this potential difference is this, right? So if the chemical, now you understand why this is called chemical potential. So if the potential, this potential is larger, is higher on system 2, then the particles are not happy. They want to flow to system 1. And they keep doing this until, so you keep doing this. Now you know this argument.